So we've learned that carbonyls are electrophiles, and really carbonyls are weak electrophiles. Unless we do something like protonate them to make them better electrophiles. So to talk about attacking a carbonyl, we need a good set of strong nucleophiles. I've also told you that our SN2 nucleophiles simply aren't typically strong enough to do this chemistry. So what are our strong nucleophiles going to be for our weakly electrophilic carbonyls? Well, we're going to talk about organometallic reactions, organometallic reagents. And these are really carbanions. Now these have a rich history. These are carbanions, no surprise. Carbon is not very electronegative. And so convincing it to carry a negative charge is not the easiest thing to do. In general, we're not going to be able to simply take some molecule that contains a CH bond and treat it with a strong base and deprotonate the carbon. And the problem is most bases aren't strong enough to do this. So we need another way to do it. And the way we do it is we actually start with a halide. So this is cyclohexyl bromide. And what we can do is, it sounds kind of odd, but we're going to treat it with metallic magnesium. And this is magnesium that's actually been shaved like in a cheese grater. They're called magnesium turnings. It's really high surface area magnesium metal. And we do this in a solvent like ether. This is an aprotic solvent. Remember, aprotic means no OH groups. And what happens is kind of a strange reaction. We're not going to go into the mechanism of it, but this magnesium slips between the carbon and the bromine. And it goes from magnesium 0, and I'm writing that this is metallic magnesium. It's magnesium in the 0 oxidation state. And what it becomes is magnesium in the +2 oxidation state. So properly speaking, bromine bears a negative charge, and this carbon bears a negative charge. Now, because this representation of an organometallic reagent, this is not just any organometallic, it's an organomagnesium reagent, and these are also called Grignard reagents, after the person who discovered them. I tend to want to emphasize the fact that this is a carbanion, but it's very hard to look at this picture and see that's the case. So when I draw Grignard reagents, I tend to draw them explicitly as carbanions, and I write the magnesium bromide as a complex counterion. And that way there's no mistaking it. This is a carbanion, and as a carbanion, it is really unstable, meaning it is a strong nucleophile. A strong nucleophile for what? Well, it's a strong nucleophile perfect for reacting with our weakly electrophilic carbonyl. So that's what we're going to make these carbanions for. Now, these aren't limited to cyclohexyl. You can do things like methyl iodide and react it with magnesium, and you'll make methyl minus magnesium iodide. You can do this on benzene rings. It's not limited to alkyl halides. It can be on benzene. Chloride doesn't always work great, but great thing on paper, everything works well on paper. So we can get these reagents, a lot of Grignard reagents. There's another class of organometallic reagents, and that's the organolithium reagents. They're really made the exact same way. You take a halide, instead of treating it with magnesium, you treat it with lithium. Again, you use an aprotic solvent. And what we get is now a lithium counterion instead of a magnesium halide counterion. Note that it's important not to use an aprotic solvent because these are strong nucleophiles. They're also really strong bases. And that goes for the organomagnesiums as well as the organolithiums. So if you have an acidic hydrogen like an OH group, your organolithium reagent is simply going to deprotonate it and you're going to destroy your reagent. So you have to keep all acidic protons, including alcohols, out of the reaction. But this is how we make these strong nucleophiles, and now we're ready to see how these strong nucleophiles react with a carbonyl.